Now that 10.4a has refreshed our memory on what polar graphs are, let's jump into some calculus and just maybe get our feet wet on that, see what happens. So let's start with this polar function, f of theta equals -4 cosine theta. We should know that to be a circle, goes through the pole, and it also goes through the point 4 comma pi. So we're going to have a diameter of 4, something like this. All right, that's f of theta. And then g of theta is r equals 2. So that's going to be another circle, also diameter 4. But this one is centered at the pole. So much different equation, creating the same sort of graph. All right, cool. So f prime of theta. We know how to take the derivative of -4 cosine of theta. That's going to give us 4 sine of theta. All right, great. And we also know how to take the derivative of 2. Oh, that's 0. All right, cool. So those are some very easy derivatives to find. So now I want to take a look at what those derivatives might give us if we actually evaluate f prime of theta for some key theta values. And then also g prime of theta for, again, some key theta values. So let's take a look here. So f of theta was, in red, -4 cosine of theta. F prime of theta was 4 sine of theta. So we'll just fill in some r values. We got r values of, let's see, cosine of 0 is 1, so -4, then 0, then +4, then 0. And then when we took the derivative and get 4 sine theta, it'll go 0 and then up to 4 and then down to 0 and then down to -4. All right, so very similar sorts of answers here. All right, and then g of theta was 2, right? And g prime of theta was just 0, so we'll just get 2, 2, 2, 2. And we'll get 0, 0, 0, 0. All right, so that was a little bit even faster. All right, but here's something that's interesting. We're very, very used to talking about derivatives and saying, oh, derivative is the slope. But that's not the full story, right? In this case, the derivative is not the slope. It should be clear that it's not the slope. For example, over here, our slope is 0 all the time? No, that can't be true. The slope is not 0 all the time on this blue circle. And in fact, let's take a look at this other place. We've got at the point -4 comma 0, which is over here, apparently our derivative equals 0, but that's a vertical tangent line. So what's going on here? These are not the slopes. These are not slopes, even though they are derivatives. So why not? And also, what are they, right? So I think that maybe a way to answer this question is to use the other notation, the Leibniz notation, instead of using primes. Remember that for the red one, r equals -4 cosine theta. F prime of theta is the same thing as dr d theta. And g prime of theta is also dr d theta, different r value, right? Okay, and when we write it like that, we can see, oh, wait a second, this is not the change in y over the change in x. This is the change in r over the change in theta. So when we find the derivative of r with respect to theta, which is what we just did, we're asking how fast is r changing as theta changes. So let's look at that blue one, for example. How fast is r changing as we go around the circle? Well, r is stuck at 2. It's not changing at all. It's a constant. And that's why g prime of theta is 0, because no matter what theta value I pick, my r value is not changing. It's constant. Now my r value is changing here because we can start, I guess we started at an r value of -4. And then our r value got bigger and bigger and bigger up to 0, and then bigger and bigger and bigger again up to +4, right? We can see that right here, from -4 up to 0, up to +4. So during this period from theta going from 0 to pi, look at how the derivative is positive. It goes from 0 up to 4, back down to 0, right? But all of this time between these two zeros, f prime of theta is positive, okay? Which means that our r value is increasing that entire time, which we can see, right? From -4 up to 0, up to +4. So a positive derivative here means that this thing is increasing. So what we're talking about is how fast r is changing with respect to theta when we take those derivatives. So another obvious question we might ask is, well, if these don't give us the slope, then what does? Okay, if I wanted to find the slope of a polar graph, then how do I do it? Well, we know that if we're looking for the slope, we're looking for the change in y over the change in x. And in fact, that's the average slope. And if we want the instantaneous, we want dy over dx. Instantaneous. Okay? So that's why this expression right here is insufficient for finding the slope, because it's not telling us rise over run. Okay? But if we recall, what we reviewed last time was that we can parameterize, basically. We didn't use that word in the last section, but we know that x equals r times the cosine of theta, and we know that y equals r times the sine of theta. So we can parameterize any polar equation very easily by getting one equation for x and another equation for y. And we've already learned how to deal with parametric equations. So how does that work? Well, we just say, okay, instead of saying r equals -4 cosine theta, we're going to take the r value of -4 cosine theta, and we're going to multiply that by cosine of theta, because that's what x is, right? X is r times the cosine of theta. So this is r times the cosine of theta. And then to find y, we take r times the sine of theta. So we do -4 cosine theta, which is r times the sine of theta. So suddenly we've just turned this into a parametric problem. So we do exactly what we used to do with those back on section 10.3. Just again. All right, so if we wanted to find, well, let's simplify this. We've got -4 cosine squared of theta, and here we've got -4 cosine of theta times the sine of theta. If you want to use a double angle identity, that might make things a little bit easier. I'm not going to, but feel free to if you'd like to. I think it's an easier way to do it. To find dy dx, we have to find dy dt divided by dx dt. And then dy dt, well, that's going to be, in this case, unless you use the double angle identities, if we use just this, then it's going to be a product rule, right? So I'm going to take that -4 out of the mix so it doesn't get too confusing. I'll take derivative of cosine is negative sine times the sine, so that's negative sine squared. And then we'll take plus cosine times the derivative of sine, and derivative of sine is cosine, so cosine times cosine, or cosine squared. This is not the Pythagorean identity, because there's a minus sign right here. All right, on the bottom, we take dx dt. dx dt is the rate of change of x with respect to, oh, I guess I should be using thetas here, right? Let's not mix our variables. And we'll start with the power rule. We'll take that 2 out front, so the -4 times 2 is -8. The argument of cosine of theta doesn't change, but don't forget the chain rule. So that's going to be the derivative of cosine, which is negative sine. All right, so this is going to be -4 on the top times, I'll just swap the order. And then on the bottom, we've got +8 cosine of theta times the sine of theta. And again, for those of you who know and love your double angle identities, we can definitely simplify this. Again, I'm not going to, because a lot of people will forget those and get confused. But if you're trig proficient, then I like that method. So feel free to do that. Anyway, so this is an expression for the change in y over the change in x, the instantaneous change in y over x, for any theta value. So this is convenient if we wanted to find the slope of the tangent line at any particular point. So they're giving us the r comma theta value of 2 root 2 comma 3 pi over 4. So we'll just evaluate dy dx at theta equals 3 pi over 4. All right? So that's going to be, well, let's reduce this. This is going to be a negative 1 over 2. And then the cosine squared of 3 pi over 4 is going to be 1/2. The sine squared of 3 pi over 4 is also going to be 1/2. And then the cosine of 3 pi over 4, well, that's going to be negative root 2 over 2. And the sine of 3 pi over 4 is going to be positive root 2 over 2. So we get 0 over, well, stuff. Doesn't matter what that stuff is, as long as it's not 0. It's going to work out to be a negative 1, I guess. So anyway, we're finding that dy dx is equal to 0 when theta equals 3 pi over 4. Okay, let's go back and take a look at this. This is our original red circle up here. 3 pi over 4, round about right there. Okay, yeah, I can buy that. That looks like a horizontal tangent line. So, so that would be when dy dx equals 0. Remember that dr d theta equals 0 over here on the far left, but dy dx equals 0 here. Remember, they're not measuring the same thing, so it shouldn't be surprising that different places give us different values. So again, to recap, to find the slope of a polar curve, first we have to parameterize the polar curve by using the conversion equations x equals r times the cosine of theta and y equals r times the sine of theta. And once we have the parametric curves, then we just do our derivatives as normal with the parametric curves.